Hello, students. We are getting into the heart of Chapter 8, where we're going to dive deeper into alkene reactions. Today is the hydration of alkenes 3 different ways. So pay attention to the different types of reagents that you use to get a desired product. And I want to show you here, there is one involving acid, for example, sulfuric acid, a mercury reagent, and a boron reagent. These are going to occur either via Markovnikov addition, Markovnikov without rearrangement, or anti-Markovnikov. So pay close attention to that. So if we just start here, we could talk about the hydration of alkenes that are acid catalyzed. Basically, you're adding water across the double bond. Acid helps facilitate this, and you can get an alcohol product where the OH is on the more substituted carbon. So that is Markovnikov addition. You can see it here. I could either write H3O plus, indicating acid and water, or I could show sulfuric acid and water, either way. If you look at the different rates of these, depending on the type of alkene you have, you could see as you become more substituted, the rate of the reaction is quite a bit faster. Based on this, could you predict the mechanism? When have you noticed things are better when you have more substituted groups? Basically, when you go through a carbocation intermediate. So the mechanism, which you will need to be able to draw yourself, involves the nucleophilic alkene attacking the acid. So here pulling off an H plus. And when you break this pi bond, you form a CH bond here, but then you're left with this carbocation, a carbon with 6 electrons, so it has a plus formal charge. That is going to act as an electrophile, and this water nucleophile will come in and attack that center, installing the O where you want it here, which will eventually become your alcohol. Be very careful not to forget this last step. Students forget this all the time. It's called a proton transfer, and you just added water, but you have this extra H hanging off. So you take another water molecule and just pluck it off, react here, that'll end up forming a hydronium ion, and then the bond here becomes a lone pair on O, and you get your desired alcohol product. So keep in mind, this can be reversible. You can add the water across the double bond to give the alcohol, but similarly, you can dehydrate this in an elimination to return the alkene. How do you favor one or the other? So what we'll find is low T is good in giving this product. High T, which involves this elimination, which is an increase in entropy, favors the reverse elimination. But the reagents that you use can make a big difference. So think about this. How would increasing the mole fraction, so basically the amount of water, mole fraction of water, shift the equilibrium? If I increase the amount of water here, would that shift the reaction to the right or back to the left? And you got to think about Le Chatelier's principle here. So if I dump a bunch of water into the system here, that's going to increase or add a stress to the system. To relieve that stress, the direction of the equilibrium goes to the right. So the more water you have, as in with a dilute sulfuric acid, the more you'll generate the alcohol product. If you use concentrated H2SO4, especially at high temp, you can favor the elimination. This is what we do as chemists. We look at what we're wanting to get, and we modify the conditions based on what we understand from chemical principles such as Le Chatelier's. Okay, let's take a look at this acid-catalyzed dehydration, and also we're going to see addition exemplifying this. You can take this tertiary alcohol, heat it with concentrated H2SO4, you could generate the alkene in an elimination reaction. Or you could do the opposite, take an alkene, treat it with dilute H2SO4, and you could generate your tertiary alcohol in the addition reaction. Be able to do both. One of the key things to help you in this chapter and future chapters is really pay attention to the reagents that are used to produce a certain type of compound. Let's look here at the stereochemistry. It's similar to the stereochemistry of hydrohalogenation. When you generate the carbocation, this is planar. So you can attack from the top or the bottom of this vacant p orbital. And so you can have the OH up or down. You will get two different enantiomers in this particular substrate. And so it's a 50-50 mixture. There's no preference for one or the other. So we call that a racemic mixture. Let's practice this before we move to the next topic. So go ahead and pause and predict the products for this one. So what we're going to do is add acid in the presence of water. So you're going to do an addition of H2O across the double bond. It's going to occur by a Markovnikov addition. So the water will add, and the OH adds at the more substituted carbon here. So you'll get your OH here via the tertiary carbocation. So you guys can practice. We'll do this in class. We'll practice the mechanism, but you can also practice the mechanism showing how you get these. So the H added here on this carbon. So that's regiochemistry, where it's going to go, what carbon each group is going to go on. So we got that down. Because this will go through a planar carbocation, the OH can add from the bottom or the top. So you get both of these. Notice that this top methyl is fixed throughout because it's part of the original starting material. So that doesn't change. So what you end up in this particular case is diastereomers because you have the second stereocenter. Okay, reaction number 2 for hydration. This is oxymercuration and demercuration. This is special because there are some times when you want to do a Markovnikov addition and you have a substrate that can do a rearrangement, but you don't want the rearrangement. So you could block the rearrangement using a mercury reagent. So meaning no 1,2 hydride or 1,2 alkyl shift will occur. And just to refresh your memory, those occur to go from, say, a secondary carbocation to a more stable tertiary. Okay, overall, look at this equation. You have an alkene. I'm going to do an oxymercuration. I'll show you the reagents later, but it'll give you a mercury acetate here. And this is similar to when you add water across the double bond. This is similar to the H. And then OH will be here on the more substituted carbon. Then you're going to remove the mercury part and replace it with an H. That's the overall process. Here's your mercury reagent, mercuric acetate. And this can essentially be an electrophile. Your double bond is going to add into the mercury acetate. And what's special about this is this locks down into a 3-member transition state. So these are both resonance structures. And this is actually similar to forming the bromonium ion. So the hybrid structure is shown here as the 3-member transition state, and that locks this in place. So because of this 3-membered hybrid, no rearrangement products are seen with substrates that want to go through a 1,2 hydride or 1,2 alkyl shift. So it'll block that from happening. What's important to note is that you do have this partial positive charge on the more substituted carbon. So when a nucleophile, such as water, or maybe an amine, or a thiol with a sulfur, will come in and attack at that center. Nucleophile attacks here, kicks open that ring, and you get your mercury on this side. So the nucleophile can be water or other things, which I'll show you. The final step is we want to get rid of this mercury. So to do that, we treat it with sodium borohydride, and effectively this whole group is replaced with an H to give, if your nucleophile is water, to give the alcohol product. I'm not going to go through the mechanism of that. What you need to recognize are the reagents used to perform this reaction and carry out this transformation alkene to alcohol through Markovnikov addition. And just to let you know, you would have formed a secondary carbocation, which would have wanted to undergo an alkyl shift to reveal a tertiary carbocation. If you can't see that, play around with that on paper. And that doesn't happen. So you can cleanly get your Markovnikov addition alcohol using the mercury reagent. Okay, let's practice. You guys try these two, pause and then unpause to check your answer. So for the first one, Markovnikov addition gives the alcohol with the OH at this more substituted carbon, no alkyl shifts, and you also get the enantiomer. You could get the OH on the top or the bottom with equal probability, 50-50, another racemic mixture. So this is just a classic oxymercuration with water. In the second one, I flip out water for an amine because N with a lone pair can be nucleophilic as well. So you'll also add at the more substituted carbon, but now instead of OH, I have NH and whatever other group here, ethyl, is on it. And then notice that in each of these, you have the sodium borohydride reagent, which is necessary to remove that mercury at the end. So if you want to do this type of reaction, you do have to write 1. That means you perform this reaction. And the reason why it's labeled 1 and 2 is that you have to complete this reaction and work it up, meaning you stop the reaction, you work it up, get your product. Maybe you purify it, maybe you don't. But then a second step, you do need to add the borohydride to remove the mercury. Okay, now we have our third and final hydration reaction. This is a hydroboration and then oxidation. This is an amazing reaction because you can add a borane across a double bond and convert it to an OH so that overall you get anti-Markovnikov addition where the alcohol is on the least substituted carbon. So you could take a long chain with the terminal alkene and add OH at the very end. Recognize these reagents. This borane here is a very reactive Lewis acid. It's shown as a dimer. And you can complex it here with a type of solvent called tetrahydrofuran, THF. And these are your reagents, your top reagent here that's being used. That is going to add boron and hydrogen across the double bond. And then later we can convert that using peroxide and sodium hydroxide to the alcohol. Let me just show you the stereochemistry. You're going to add the H and OH, and it was really a boron before, which is converted to an OH across a double bond. And notice that they're syn. And what's syn? Pay attention. The H and OH are syn, either both up or both down. So that's what's key about this reaction and the stereochemistry. The anti-products where the H and OH are one up, one down are not observed. So this cleanly gives syn addition, syn on the same side. The reason is when you add BH across the double bond, it goes through a 4-member transition state. The reason why it's anti-Markovnikov is the boron part is bigger than the hydrogen. So it wants to go away from the bulkier group to give you this. And so you're having the pi bond attack boron from the less substituted end, and the hydrogen is transferred. It goes through this type of 4-member transition state, the same as above, but here I'm just showing this green is bulkier boron. Here's the bulkier, more crowded end. So these want to be as far away as possible. This anti-Markovnikov transition state is preferred versus this more crowded less preferred Markovnikov addition. Just to let you know, the mechanism proceeds so that this is repeated 3 times to give you a trialkyl borane, and then you use hydrogen peroxide and hydroxide to add the peroxide onto the boron. Then you get a transfer of the alkyl group on the O. This, upon treatment with hydroxide, releases the alcohol product, and this happens to give the trialkoxyborane. I don't want us to get too lost in the details of this mechanism, so you can, if you're that interested, you can definitely look in your book for further info, or I can give you more information on this, but I'm not going to test you on the specific mechanism. But you do want to know that it's syn because of this 4-member transition state, and also it's anti-Markovnikov because of that as well. Okay, so stereochemistry. You can attack from the top or the bottom, but the H and OH will always be syn on the same side. So here I have the OH up, and there's an H here up, but that's not a stereocenter. So depending on your starting substrate, you could get enantiomers out of this, or you could get diastereomers. So in this case, you get a 50-50 mixture of enantiomers. Let's practice here on our final concept check. Take your time, sit down, write, predict the products of these. Be very careful with the stereochemistry and see if you can identify, are these enantiomers or are these diastereomers? So pause and do that. So for the first one, what we're going to see is we're going to add boron across the double bond, B and H. The boron adds to the least substituted side here, and the hydrogen here. The boron will then be converted to an OH. So the H and OH are syn. They're either both up or both down. And that means if the H is down, then the other group was up here. So you get a pair of enantiomers. The easiest way to do this is keep the chain, the skeletal framework, the same. Basically the parent chain the same here. And then make sure your H and OH are syn, both up or both down. In this lower product, again, consider the regiochemistry. OH will be on the less substituted carbon, H here. This upper methyl is fixed, so that doesn't change in your products. But notice that OH and H are both either down or both up. And if the H is down, that means the methyl is up here. If the H is up, the methyl is down. So in this particular case, because you did have multiple stereocenters where the methyl is up, and then you have the OH down and methyl up, here we have up, up, down. So these are diastereomers. Okay, that's all I'm going to talk about in this video, and then we'll continue with more alkene reactions next time.